Hmm. Halo, 之前 post few question on the forum. Maybe you guys can take a look if you haven't. See if you can answer to those questions or not. Wait maybe 2 more minutes for the rest to come. Then we'll discuss. I'm going to a Moodle and then 之前 post some question there. See if you have the same problem or you think you don't know how to solve it. Syed now with you today. Welcome to him. Okay. Anyone have idea of the first one? Or is this question valid or not? What's the question two? In question two, when I use the definition of group on the set X proof to prove the existence of the left or right identity. Otherwise, how should I prove they both exist? Okay. So question one is asking about how to prove existence of identity, left or right identity. Okay. So how's my question two read? So first I gave you definition of left and right identity, right? So basically I break the identity definition to two parts. Okay, one equality is left, one equality is right. And then I say that a priori a left identity and right identity don't have to be the same, right? Uh, because yeah, because we don't impose that. But I ask you to prove that they must agree. Okay, so what's my wording here? So my wording says that prove that a left identity and a right identity of a set must agree. Okay, so I just say they have to be the same. Prove that they have to be the same. Okay, uh, I didn't say there is a unique one. Okay, so you just need to prove for uniqueness. Okay, so if you want, maybe this question can put a comma if exists, if they both exist. Okay, but um, doesn't care. Yeah, whether it exists or not, by this definition, they must agree. Okay, they must agree whether they exist or not. Okay, we don't care about existence. Okay, so this wording of the question doesn't say has left identity or right identity. Is it clear? You just need uniqueness. Okay, doesn't care whether it exists or not. Whether it exists or not exists, it still have to be unique. Okay? Statement you need to prove. Clear? 之前 okay Okay, how about the second part? In question 2, does to prove they agree means we have to prove the existence of so this is almost the same question. Yeah, so just agree. Okay, agree. Don't need exist. They don't exist, they still have to agree. Whether they exist or not, they have to agree. In question 3 is delta square means doing the operator on two same delta or just the usual delta times 2 times. Okay. So in this question here, this delta is anything. Okay. Just a product of delta. What kind of delta? I don't care. Whether it's a function, whether it's a number or not. As long as you can compose them. Okay. So the key point here is the uh, invertibility. Okay, invertibility is enough. But apparently, so the fourth question here is a good one. So in question 3, is the delta in a group. Okay, it can be solved by here solve it to put a D here. So solve it to put a D here. I heard that your statistic class is like an English class, is it? Yes or no? Need to check grammar or stuff. This is I heard. I don't know. So please here solve for the D. Then Thursday I don't teach you. Here be solve. Solve have a D. Okay. D solve. Need to put a D. By the associativity property. The thing is not ensure that okay property have the property. Okay, good. So this is the right one. Okay. Yeah. So for actually for question 3, you need associativity. Similar to what we did in the class. Okay, so um, um, okay, I will add the inner group into this question. Okay, inner group. Okay, so this is true inner group. Okay, we need associativity here. Right. I will make changes to this assignment sheet. Okay. Yeah. Any question or not? Any other question when you read the assignment? Question not clear when you read. When you try to do big problems. Or did you try tutorial question? I would straight away provide you the tutorial question again because you have a past tutorial question. I already give you the solution. So if you want to do the current tutorial question, please do it, and then I will check for you. Okay. If the answer I have a different answer, then I will provide. Okay. Yeah. If you do, then I can check. Okay. No question. Okay. I think we shouldn't waste too much time. Okay. So let's go into uh, symmetry group today. So we will look at one very important example symmetry group today. Part of my research is heavily related to symmetry group. Yeah. So let's look at the symmetry group. So today we'll talk about symmetry group. So to talk about symmetric group, we need to introduce the definition of permutation. So you should recall from your discrete math the permutation combination topic. Okay, what's the P, what's the C? Okay, but now today we look at P, okay, permutation. So what's the permutation of a set? Okay. So last time we had set, and then we both stop reading the set, right? Okay. Now, what's the permutation of a set? Okay. So permute, right? So you need to change the order of your set. You change the order of your set. Okay. So what's the key property when you change the order of your set? Okay, you swap position, right? Okay. What's the property? Can you swap it back or not? If you know how to swap, how to swap the position. Okay. So for example, did you know a trick, a cup trick? For example, if I swap it, can you swap the position back? Okay, how about like this? So there's a trick like you put a coin into a cup, right? And then I swap the cup around. And then can you find the coin back? Can you find the cup with the coin back? Ah, reverse the process, right? Again, reverse the process. Did everyone know what I'm talking about? Okay. Okay, so you have a few cups and then you cup a coin and then you swap. And then tell me which one, where is the coin now? Right? Okay, so this is a permutation. Okay, so a permutation of a set is a projective map, okay, from X to X, okay, from the set to itself, okay. You cannot suddenly swap, and then take the cup away or put an extra cup, right? Okay, so otherwise you are cheating, correct or not? Okay, so this is a bijection from the set to itself. Okay. So what is symmetric group? So the set of all permutation. Okay, I take all permutation. So permutation to do on the set. Okay, so what kind of set we are interested? Okay. So you will how you recognize each cup. Okay, maybe you recognize, oh, this one is the first one, this one is the second one, this one is the third one, this one is the fourth one. Okay. So we're interested in the set of permutation of the indexes 1 to n. Okay, we swap around 1 to n. Okay, and then this is called a symmetric group. Symmetric group denoted by Sn. Okay, so so what kind of elements is in there? For example, right? For example, when n equals to 4, okay, I have 4 items to swap, right? Okay, 4 items to swap. Can I swap like 1, 3, 3, 2 or not? Do this? Why not? 可以 啊 Why not? Can I do this swap? Cannot. You say no, right? Why not? Not symmetric? No. Anyway, not one to one. Okay, not one to one. This is not a bijective map. Okay. So for example, we can do like 2, 3, 4, 1. Okay, for example. Okay. So I said that this is symmetric group. Okay, so we really mean it is a group. So to satisfy a group property, what do you need? What are the three properties of a group? Huh? LOC. Okay, you need to be able to compose. Okay, and what else? Identity, invertible. That's all. Uh, it's associative. Okay. So first of all, is the LOC associative here? What's the LOC here? Huh? How P compose? Oh no. What's the permutation? Type definition. What's the permutation? Set of function. Huh? Function. How function compose? Is composition of function associative? We prove that, right? Okay. Function composing is associative. Any identity here or not? What's the identity element in this group? Huh? What's the identity element in this group? What function is an identity? Huh? X. Mm, X. Px equal to X. So you send 1 to 1, send 2 to 2, send 3 to 3, send 4 to 4. Okay, this is the identity function. Okay, and then, so let me write down what I have said. So Pi send to I is the identity function here. Okay, does inverse exist or not? Why? So because it's a bijective function. Okay, so inverse exists. Okay, but so how we write down the inverse uh, and how we write down composition in this group? Okay, we will see in a moment. Okay, we'll see in a moment. So one very convenient way to write down this map is called a cycle notation. Okay, we will write it as this notation. Okay, we don't want to like keep track, write this table each time. So we can write it as 1, 2, 3, 4, for example, for this map. What do I mean by this? So this cycle notation encode how we do this map. Okay, 1 gets sent to 2. Okay, and then 2 gets sent to 3. So we write 3 at the side of 2, and then 3 gets sent to 4. So you write 4 after 3, and then 4 sent back to 1. So you repeat the loop. So we close. Okay, so we close. Does it make sense? Okay, so you don't write 1, 2, 3, 4, 1. Okay, since 1 repeated, so we close the loop by using the bracket. Okay, so this is a cycle notation. So we use cycle notation to do computation on cyclic symmetric group. Okay, you want to see one more example on doing this cycle, how to write the cycle notation, or you okay with it? One more example. Um, how big you want? Not too big. How big do you want? How about do 5? Yeah, let's do 5. How about just do 3 then? Just do 3. Okay. So yeah, so we permute this this 3 number. So how should we permute it? Mm, maybe we write 3, 1, 2. Okay. So what do you think is the second notation for this map? I'll try. Jiawen, what's the cycle notation for this? Sorry? 1, 2, 3. Okay, let's check. 1, 2, 3. Did you say 1, 2, 3? Okay, let's check. So this says that 1 sends to 2, right? Okay, but here 1 sends to 3. Okay, so we should have 1 gets sent to 3. Okay, and then 3 gets sent to 2. And then 2 gets sent to 1. So we repeat that. So we close this. Okay, get 1, 3, 2. Okay or no? Okay. Okay. Need one more exercise or not? No need. How about the rest? Okay. Can follow? Can follow? Question? One more example. Okay, test one more. Okay, let's go to 5. Okay, one more example. How about we do it differently this time? Okay, we go from cycle notation back to see what kind of map is it. Okay, let's do 1, 5, 4, 2. Okay, so what does this cycle notation give? 1 have to send to where? 5. 2 have to send to where? 1. 3 have to send to where? 4. 4 have to send to where? 2. 5 have to send to where? 3. Okay, so you go from 1 to 5, 5 to 3, 3 to 4, 4 to 2, and then 2 to 1. Okay, make sense? Make sense? Okay. So this is how you go back and forward between cycle notation and then see where's the map, what's the map doing. Okay. Okay. So the definition. Okay. So what's the definition? So a cycle. Okay. So we got L1, L2, L3, and so on up to Ln. Okay. So these Lj is in the indexes of 1 up to n is an element, okay, in Xn that sends ij to ij plus 1. Okay, ij plus 1 mod n, because we need to do it as a cycle. Okay, for all j in 1 to n. Okay. So we send from ij to ij plus 1. Okay, and then mod n, because we want to come back. Okay, mod n. Need to return after the bracket. Okay? Can or not? Can. Okay. So the remark here, okay, I think you should have some doubt in your mind. Okay. So let's write down something here. A remark. So the cycle notation is not unique. The cycle notation here is not unique. Why is it not unique? Just like I say, it closes as a loop, right? So if you have a line, if you have a loop, okay, you can show the loop, show the bottom loop, or show the top loop, right? But they still represent the same loop. Okay, what do I mean by this? So for example, okay, for example, 1, 2, 3. Okay, I also can write it as 2, 3, 1. Right or not? Let's think about what does this mean. 1 gets sent to 2, 2 gets sent to 3, 3 gets sent to 1. Okay. Okay, not coming. Okay, so you can see that on the right hand side, 2 gets sent to 3, 3 gets sent to 1, 1 gets sent to 2. It's the same. Same or not? Or you don't believe me? 1 gets sent to 2, 2 gets sent to 3, 3 gets sent to 1. Again, on this side, 2 gets sent to 3, 3 gets sent to 1, 1 gets sent to 2. Are they the same? Okay, I think we need to do the kindergarten journey. So like this. Right. So they are the same. Okay. So you can like write it, start with different indexes. They will give the same map. So that means we don't need always to start with 1. But for easy computation, prefer we prefer nothing, never mind. Second, how about identity function? How do we write the identity function? Okay, so it is customary that we write just bracket 1 index. Okay, if it doesn't move, this index doesn't move fixed by the permutation, we just put like this. If the index I is fixed by the permutation. You can write this, but in a real practice, usually we don't care. Okay, usually we don't care. We just remove it. Okay, because we don't want to waste time. So we typically remove it. So I will show you the example in a moment. Okay, don't nervous. Okay, so let me show you an example. So for example, I can put 1, 2, 3, and then put a 4 here. Okay, this means what? I have 1 sent to 2, 2 sent to 3, 3 sent to 1, and then I fix 4. Okay, so meaning 1 gets sent to 2, 2 gets sent to 3, 3 gets sent to 1, and then 4 gets sent to 4. Okay, but usually we don't write this anymore, we just write 1, 2, 3. Okay, so here I already put a problem to you. Okay, you see, 1, 2, 3 is a permutation in S3. Okay, you permute 3 elements, but you can realize it as a permutation in the higher end. Okay, where you fix all the rest. Makes sense, right? Because I also can realize it as a 1, 2, 3 fixing 4, fixing 5. Okay, but this one is in X5. This one is in S4. And 1, 2, 3 itself is in X3. Okay, so every time you see this cycle, right, you should ask which SN you live in. Okay, you should ask which SN you live in. Yeah. In fact, this is a very good property where we can study SN all together. Where we can study SN all together. Okay. Okay, so this is notation. So how about I fix everything? Should I write like all the one index now or not? I fix everything. And then fix everything. Okay. You see, such a long list. Okay. Maybe we just denote it as an identity function is enough. Okay. Yeah, don't need to write so many bracket number. Okay. Okay. So these are notation. Okay. So after we learn this notation, so let's look at some special cycle. Okay. So for example, one cycle is not interesting already. We don't even want to write it out. So 2 cycle is interesting because 2 cycles start to do something different. Okay, what does the 2 cycles do? So 2 cycle is like containing 2 indexes in the bracket. This is called transposition. Okay, you know why is it called transposition? Because it swap the 2 indexes. Okay, I1 to I2, I2 to I1. Okay, so for example, what kind of transposition you have? For example, you have 1, 2. Okay, so you send 1 to 2 and then 2 to 1. So you swap the two, uh, swap the two index. Sometimes diagrammatically we will draw like this: 1 to 2, 1 send to 2, 2 send to 2. Okay, diagrammatically you can do this. And where's Ming Xiu? Why? Morning call him. Him tag him. Okay, 1 to 2, 2 to 1. Okay, sometimes we can draw it diagrammatically. This is the map. Okay, next. So this is the transposition. I think transposition come up in your assignment, right? I think you see this in your assignment. Okay, so this is transposition. Okay, so next is two disjoint cycle. Okay, so when does two cycle are disjoint? What do I mean by two disjoint cycle? Okay, so if you have two cycle, they are disjoint. That means they have nothing to do with each other. Okay, meaning all the indices are not the same. Okay, once. Okay, for all P in 1 to n, and, Q in 1 to n. And so, for example, one. Let's give an example. So, for example, 1, 2, and 3, 4. 1, 2, and 3, 4 in Sn are disjoint. Okay, they don't have any. Um, they don't affect each other. Can I say like that? I cannot say so. So you can see that the first map has an effect on 1 and 2, but the other only has effect on 3 and 4. Okay, so they are disjoint. Okay. Why I'm interested in this? Because later we will soon take a product. Okay, we will soon take a product of them. Okay, so let's tell you how to take product first, and then you will see why this definition makes sense. Okay, so let's take a product. So how to take? Well, how to take of two cycles. So how to take product of two cycles? For example, let's take product between 1, 2, and 2, 3. Okay, 1, 2, and 2, 3. So actually, these cycles are just what? What's the first definition? These are permutation. These are just bijective function, right? Okay, so in principle, what do you do? You should check. You should check what? So this is in S2, S3. Okay, so you should check where the 1 gets sent, where the 2 gets sent, where the 3 gets sent. Right? Okay, because you want to see which function is this. Okay, so let's check. Remember the table we started with? 1. So if we first do 2, 3, what happened to 1, 2, 3? 1 gets sent to where? 1 gets sent to where? 1, right? Fix 1, because this is just equal to 1 times 2, 3. 2? 2 gets sent to where? 3, right? Okay, 3 gets sent to 2. Okay, but we need to compose 1, 2, and 2, 3. So what happened if we do 1, 2 to 1, 3, 2? 1 gets sent to where? 1 gets sent to 2. 2 gets sent to where? 2 gets sent, 3 gets sent to where? 3 get fixed, right? So this is 6 times 3. Correct or not? What question? What question? Yeah. Hmm? Question? Mm-hmm. Why wrong? Yeah. So 1 sent to 2, 2 sent to 1, and then 1 sent to 2. So okay. I mean, okay. So I'm composing. How should I do it? Okay, maybe throw this line. Okay, throw this line. So I compose it this way. Uh, mm, hmm. Okay. I know what's going on here. So let's draw it another way. Okay, let's draw it another way. Maybe this way will be clearer. Okay, let's draw it this way. Okay, so first we do 2, 3, and then here we do 1, 3, 2, and then we compose map, right? We compose with 1, 2. Okay, in this case here, 1 gets sent to 2, 3 gets sent to 3, 2 gets sent to 1. Is it clearer now? Clearer now? Okay, let's draw this. I'm confused. Okay, okay. Yeah, so if you compose this map together, what kind of function you get, in fact? What function you get? 1 gets sent to 2, 2 gets sent to 3, 3 gets sent to 1. Okay, so we check that 1, 3 is actually 1 to 2, 2 to 3. Okay, okay. Uh, yeah, so, okay. So let's do another one. Okay, let's do another one. How about 1, 2, and then 3, 4? Okay, so we are taking a product of disjoint cycle. Okay, so product of disjoint cycle. So let's see what happened here. So we have 1, 2, 3, 4 in this case. And then we do 3, 4 first. Okay, our composition start with right. So 3, 4, what happened to 3, 4? It fixes 1 and 2. Okay, and commute 3 and 4. Okay. And then next we do 1, 2. And 1, 2 fixes 3 and 4. Okay, but swap 1 and 2. So altogether you have what? Altogether you have what? You have 1, 2 swap and 3, 4 swap. Okay, but how do you write this down? How do I write this down? So first, I check where is 1. 1 to 2, okay? 2 to 1. So I have to close the bracket. And then I start again. 3 goes to where? To 4. 4 goes to 3 again. And then I close. Okay? So you see, if I do the product of disjoint cycle, I still get a disjoint cycle. Okay? So this is why we call them a disjoint cycle. So you cannot combine the cycle. That's why we call them disjoint cycle. Okay? Yeah, because their permutation uh, is not there's no overlap. Okay, but you see, the first one is not disjoint. Okay, because they both have some effect on 2. Okay. Okay, so how about think from here? Is there a way to get this product or not? without checking this? Do you know? Do you know how to do this product here? Okay, so what can you do? Okay, so similarly, in this example, right, you need to check where 1 gets sent to, where 2 gets sent to, where 3 gets sent to. Okay, so let's look at this product here. Okay, 1, 2 composed with 2, 3. Okay, we need to know where 1 gets sent to. So in this composition here, which one has effect on 1? First one or second one? Huh? First one or second one has effect on 1? First one, right? Okay, so 1 gets sent to where? 2. Okay, so first 1 gets sent to 2. Okay, and then uh, we stop here. Okay, then we need to check where 2 gets sent to. Okay, first one or second one has effect on 2. What? Sorry? Both, right? Okay, but which one we care first? Second one, because we apply the second one first. Okay, so 2 will be get sent to 3. Does first one has any effect on 3 or not? No. Okay, so 2 will stop at 3. Okay, and then 3 gets sent to where? In this composition. 3 gets sent to 2. Okay, but can we stop here or not? Why not? Because we still have another composition to do. Okay, 3 gets sent to 2, but 2 gets sent to 1. Okay, then we can stop. Okay, because there's nothing happen with 1 anymore. Okay, so 3 have to send to 1, so we close it. So we get 1, 2, 3. So it's the same answer here. 1, 2, 3. Okay. How about we do one more exercise? We do one example, see whether you get the computation or not. Okay. So let's do this example. 2, 3, 4 times 1, 2, 3. Okay. So how to do this computation here? Okay. So which number you want to start with? 1. Okay. Let's start with 1. Okay. 1 gets sent to where in this composition? 1 gets sent to 2. Okay. But 2 will be sent to different place again. Okay, under the whole composition. So 1 gets sent to 2, okay, but 2 will get sent to 3 eventually. Okay, then we can stop at 3 because there's nothing affecting 3 anymore. Okay, so 1 will get sent to 3. Okay, how about 3? 3 gets sent to where? 3 gets sent to 1. Okay, does 1 get sent to anywhere else? No. Okay, so we can stop here. So 3 sends to 1. So this means we have to close the bracket. Okay, we close the bracket. How about, so what's the next thing we need to check? We already know 1 and 3. So who else we need to check? 2 and 4. Okay, let's check 2. So 2 gets sent to where? Okay, in the first composite function, you send to 3. But 3 gets sent to 4 again. Okay, in the next function. So should we stop here? Yes, right. Okay, because there's nothing happening to 4 anymore. So 2 go to 4. Okay. So where does 4 go? The first function has nothing, is fixing 4, right? Okay, but the second one send 4 to 2. Okay. So 4 will get sent back to 2. So you close the bracket. Okay, you finish the loop. Okay. And you can go back and check. Okay, please check. On function wise, is it true? Okay, so you check whether on function wise, is it true? Is it true that you get this disjoint function, disjoint cycle? Okay. Okay, go back and check. Okay, homework, check whether what we get is true or not. Okay. Understand? Do you know what you need to check here? Apply the first function and then to 1, 2, 3, 4, and then apply 2, 3, 4 to the domain again, and check whether you get 1, 3, and 2, 4. Do you want one more example exercise? Yes, okay, let's do one more. How about do a little bit more? 1, 2, 3, 4, 5. Okay, I don't. 1, 3, 2, then okay. Yeah. So which one should we check first? Start with 1. Okay, let's start with 1. So what happened to 1 here? 1 go to 3. 3 go to 2. 2 go to 1. So we stop at here. 1. How about 2? Here, no effect on 2, fixing 2. So second one has effect on 2. So 2 goes to 1. And 1 goes to 2. So 2 got fixed as well. Okay, how about 3? 3 goes to 1. 1 goes to 3. And there's no effect on 3 anymore. So this is actually a identity map. Okay, so if you don't believe, right, go and test this out. Okay, go and test this out. Do the 3 composition. Okay, go and do this composition, and then you should get 1, 2, 3 back. Okay, go and check. Okay, happy? Happy or not? Any question? Any question? Any question? No? Okay. Question? So you should check that this is actually an identity function. Okay? No question. No question. How about we take a break until 9 o'clock? Hey, call me still coming.
那 left identity 的这但是例子，因为我其实有找到，就是有
也可以啊，也可以啊。
那也是
哎，喂，等一下，等一下。哦，你是讲如果，但如果不存在就没有讨论的。讲啊，对，不这样讲，不这样讲。哎，我再想一下，你再问什么？你是说如果一个不存在的话，这个题目不成立？
不懂。哦，没有，我问，
比如说这个题目到底要不要存在才成立啊？
它如果存在，那我证明了。
没有，I mean 讲讲呀。等一下，我想一下。
哦，
你的问题很刁钻。这个刁钻，他在问要不要等下你讲有一个 example 是有 left identity 没有 right identity，对不对？什么？你给我大家怎么样？
好像我可以大 B 的 AB，
哦，你自己 set 的哈，自己 set
对啊，那就可以了。
没有啊，目前的 E star B，难道你下一个东西是 E star B 等于 B，但是 B star E
第三也就是一样，就永远是第二个很对啊，这样子就很公式。
呀，E star B 是 B 嘛，对不对？
哦，
B star E 呢
反正 A star B 一定是第
？E
二个
star B 哦，B star E 是 E 啊，
类似。
嗯，E 是 B star E 是什么？
是一打开的，
的 left identity 是你的 left identity，对，嗯，你是说写一下？你讲什么？
我是讲 A 的，就反正 A B 是好。
OK，这个要 B，这个要 B，对不对？所以 E is left identity，或者 B is 嗯，这个是不是会造一个 contradiction 出来？
啊，没有，因为它的 identity 没有讲到有变成。
哦，你是说可以有不同的 left identity，是不是？因为 E 是 left identity，B 又是 left identity 啊。OK，然后呢？啊，然后
没有，我问这样子对有没有问题？
对 agree 有没有问题？要有问题的是，如果 left 跟 right exist，它是 left 不等于 right 哦。
那没有思想，这在不可能。
要这样讲，是你如果要这个对的话，在我的 setting 里面，这个也要对。对，假设你这个 group 就有两个东西啊，
啊，对对对呀，
然后你也要有这个东西。
对，
哎，好，可以。然后嘞，
所以有 left 没有 right 是没有问题。嗯，
没有的东西就 recklessly true。没有啊，没有问题啊，没有问题啊。有 contradiction to 那个 statement 是说，如果他们存在但是不有力，这样才有问题。这样没有存在就没有问题。我就在那请你。Yeah, let's take attendance before we start. Venus 那天，OK，Winter, and Winter you just woke up. Did you just wake up? Did you just wake up? OK，上颚，应该说上颚的，就是上颚眼，吃鱼，吃鱼眼，OK，金星，俊岭，海人，金峰，OK，七峰。Hey, Shimon, why you need to come to the first one? I don't understand it.
What do you mean by tag attendance? What kind of things is that? What's the drop form? What's the drop form? The course you need to do the first attendance. Ayo, I think it's a kind of like how to say paperwork or something like that. I don't. It's stupid or like that. Huh? 200. No, there are two practical. Actually, no need to do this kind of stuff. Y in T 胸一起 OK 可以减盐加叶，应该说加叶二 OK 本数一定誉为燕博燕临近临近 OK 总结一周定于柳晴 OK 登城中明力燕 OK 子谦啊德先英英德先英英掉 Grace 彩燕，哎，我也彩燕啊，彩燕，我也彩燕，是啊，是是，no disappear。第二个明秀哎，is he coming or not? On the way 啊，traffic jam 啊，Michelle，yeah, Ryan, Ellie, yeah, Ellie 哎，just woke up 啊，traffic jam，永志，哦，永志是他跟你吗？OK，雪梅，子源，诶，终于说子源是当然，子源，我不要考点那个 Raylan，严科。哎，严科有 miss first week，OK，泽瑞，OK，哎，严科 I thought you are graduating. Have you graduated? No, not yet. I thought I marked your FYP. I don't. Huh? So I thought you graduate. Are you supposed to graduate? Huh? Are you supposed to graduate? You finish your FYP, right? Yeah. So what is your plan now? Like what's your study condition now? Situation? Huh? Just this course? You just need to retake this course. Okay. For those who retake, who class? Is it Zeri? Are you retaking? You retake, right? So if you have any problem, just ask me. Okay. Or see me in the office hour. Okay, I know our class is pretty early, right? So if you say you really have a difficulty to wake up, okay, maybe I can give you freedom to be late until maybe 1 hour at night. But but you need to note that we are 2 hour class. So if you come at 9 hours, then 1 hour you have to go again. So you need to be aware. So since this is a early classes, right? So please make sure you rest earlier. Okay. Otherwise, a lot of people tell me I got headache, headache. So young already got headache. How to do all? Right. So rest earlier. Okay. Yeah. Rest earlier. Okay. Don't play games and don't chit chat. Please rest earlier before the class, before the early classes. Okay. All right. Let's continue. So let's continue. So let's collect what we said just now. So if we have a two disjoint cycle in Sn, then we can really commute the cycle. Okay, we can commute them. Okay. So in principle, function composition is not commutative, right? Last time Ziqian gave an example already. Okay, it's not commutative. But if the cycle are disjoint, it is commutative. So for example, what? Just now we have 1, 2, 3, 4, right? Okay, so we can really write it as 3, 4 times 1, 2 is the same, right? Because they have no effect on the same index. Okay. So first one fixes 1 and 2. The second one fixes 3 and 4. Okay? So they don't have effect on each other. So you can do whichever one first. Does it make sense? Okay. Okay. Yeah. So if you don't believe, right, how to check? How to check this equality? This is an equality of what? F. How with that? Equality of what? Equality of what? Equality of what? Function. Okay. How to check? They are the same on function. You need to apply on every element in the domain. Why so many people keep coming to the wrong room? Okay, next time we do an open A one. Okay, function. How to check function? Need to apply on every element in the domain. Okay, what are the elements in our domain here? This is in which S4. Okay, so we need to check what happened to 1, 2, 3, 4. Okay, you need to check that they have the same effect on 1, 2, 3, 4. Okay, yeah, so they should have the same effect. Can you straight away see or not? You without writing first, you should first already see it. Okay, so first you swap 3 and 4, fixing 2 and 3, fixing 1 and 2, and then you fix 3 and 4, and then swap 1 and 2. Okay, so let me write different color. And then on the right hand side, what you do first? You swap 1 and 2 first. And then you do 3 and 4. Okay, so what's the difference between these two? Okay, so the difference is the order you do the swap, do the transposition. Okay, so this color is the difference of the order. They are the same, but what is the difference? They are different. What are the same? What are they the same? Okay, so this is a very key concept in abstract algebra. Okay, they are different. They are the same. When I say they are the same, but why do you have a left expression and right right expression. So there's different in what way? And then we disregard this difference. Okay, we don't care about the order now. We just care about the end product. Okay, sometimes there are differences, but what are the similarity between them? Okay, this one we will see in future. But for now, they are the same. Okay, they are same as function. But what's the difference between them? It's the difference of applying them. Okay, the order we apply them. Okay, next. So next, very useful theorem. Okay, so this is a very useful theorem in a symmetric group. So any cycles, okay, any cycles in Sn n greater or equal to 2 can be written as the product I think I don't want to show you the proof yet. I want you to believe the statement first. Okay, just now we have done one example, which is 1, 2, 3. Okay, just now, how do we write 1, 2, 3 as? Do you still remember? You want still recall in the first hour what we did? What is 1, 2, 3? 1, 2 times 2, 3. Okay, I can write cycle as a product of transposition. Okay, so in fact, why are you late? Huh? You have a very bad night. Ryan also have a very bad night. Okay. Yeah, both of them have a bad night together. I'm not sure it's physically together or mentally together. Okay, never mind. So 1, 2, 3 is 1, 2 times 2, 3. Okay, 1, 2 times 2, 3. Okay. So the theorem here is any cycles, okay, you can break into product of transposition. Okay, so how to do it? So how to do it? How about I let you think for 1 minute, see if you can figure out in general. Just use this example, is enough. Can you guess the general form? How to split using the example I show you? Any idea, Hisham? A1, A2, A2, A3. Okay. So you should check that the left-hand side and right-hand side do the same mapping. Okay, so you should check that as do the same mapping. Okay, do they send the domain to the same image or not? Okay, you should check. Okay, check on both sides. Okay, actually, there's another way to split. There's another way to split it. Okay, there's another way to split it. So another way to split it is this way. So similarly, I can write 1, 2, 3 as 1, 3 and 1, 2. Okay, can you check? Can you immediately check this? So 1 gets sent to 2. Okay, there's nothing about 2 here. 2, 1 gets sent to 2. So 2 gets sent to 1. Okay, gets sent to 1. And then 1 gets sent to 3. And then nothing happened to 3. So it's like 3. And then 3 gets sent to 1. So we close it. Okay, so this is another way to split the transposition. Okay, so in this case here, you should think like this 1, right? It's like a bridge. Okay, it's like a bridge. You see, 1 to 2, and then 2 to 1, and then 1 to 3. So it's like a bridge to the next function. Okay, it's like a bridge. So you see this cycle combine the bridge together, or you split sometimes into disjoint cycles. So another way to write down this product cycle is A1, AN, and then A1, AN minus 1, dot, 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 A1, A3 times A1, A2, like this. Okay, so there are two ways, at least two ways to write it down. Okay. So to check, how to check? This is a equality of function. Okay, so you need to check on the element, apply to the element. Left and right should do the same thing. Make sense or not? Okay. So for this kind of n, right? This argument for n, you should start with doing smaller n first to see it. Maybe when n equals to 3. Okay, to see that this segment is true. And let's try if you can generalize your idea to larger n. For example, n equals to 4. Does it still work? 5 still work? And then prove it for all n. Okay, so you should start with a small n first. You see, our n start with where? Start with 2. Why not I start with 1? Why not I start with 1? Yeah, the permutation of one index is 1. It's just 1, right? You cannot move it around. Okay, so there's no transposition when n equals to 1. So starting from n equals to 2, you have the transposition. Okay, n equals to 2, what element you have in x2? You have the identity function and transposition 1 and 2. And then 3, you have how many elements? How many elements? So in x1, you got 1 element. x2, you got 2 elements. Order 2. S3 got how many elements? Permutation of 3. 6. How to get 6? 3 factorial. So in general, Xn has how many elements? N factorial. Okay, so these are all finite groups. Okay, good. Okay, next. Next. So next. For next theorem. If a cycle can be expressed as the product of an even or odd number of transposition, then any other product of transposition equal link to that sigma. Did I put sigma here already? In the second, okay, I should put a sigma here. Okay, equaling to the original cycle must also an even or odd number of transposition. Okay, what does this mean? Okay. Okay, and now I want you to learn to read statement and then try to predict what it says. So if a cycle can be expressed as a product of an even number of transposition, then any other product of transposition equaling to the sigma must also contain an even or odd number of transposition. So you should read this statement as even, even, and odd, odd. Okay, replace the even by odd. Okay. So what does this mean? For example, just now, okay, 1, 2, 3. We can write it as product of transposition. This is guaranteed by the theorem just now. Okay, and I show you how to do it. Okay, there are actually two ways to do it. But did you realize that the both way you do it, you both have two cycles? you realize? There are two cycles. Both of them are even. Okay. Both of them are even. Okay. I cannot suddenly pop up another maybe 1, 3 here. Okay. This will change my cycle. Okay. But this theorem doesn't say they have to have the same amount of transposition. It has to be even if it is even. So meaning what? Okay. Meaning I also can write something like this. Also can write something like this. Can you see that this is the same cycle? Huh? Can you see? Why? Why are they the same? 1, 2, and 1, 2 is what? Identity, right? 1, 2, 1, 2 cancel each other. Why? The first one swap 1 and 2. The second one swap it back again. Right? So you did nothing. Okay, so actually the inverse of the transpose is the transpose itself. Okay. Yeah, the inverse of the transpose is the transpose itself. Okay. So what I want to say is 1, 2 inverse is just 1, 2. Okay. If you want to write 2, 1, doesn't matter. Okay. 1, 2, 2, 1. Okay. So a cycle can be expressed as a product of even number of transposition. Then any other product must be even number. Okay, so this is the key of the statement here. If it is odd, then it is odd. Okay. But this class is a proof class, right? Okay, I think we should prove this, but I don't want to do it today. I think you will be blurred, but we will do it in next class. Okay, so let you accept the fact first. Okay, you accept the fact first, and next time I tell you, you are more ready to accept it. Okay, otherwise you will confuse, I think. Okay, so product of even numbers of transpositions is always equal to a product of even transposition if they represent the same cycle. Okay. Okay, let's prove it at the start of next lecture. Does everyone understand this statement, or you have question, or you want to challenge this theorem? You should challenge theorems, okay? As a mathematician, don't believe. Okay, what you believe is only proof. You only believe in proof, not statement. Okay? You should challenge. Okay? Yeah. Any question? No question. Okay. So why is this important? So this is very important actually. So we can define an invariant on Sn. Okay, this is the first invariant you will see now. Okay, this is an invariant of Sn. So what kind of invariant we have? So in algebra, we like invariant. You see, there are so many number computation we are doing. So what is unchanged inside this calculation? Okay, what is unchanged inside the structure? Okay, we are interested in invariant. Everything is changing. What is unchanged? Okay, so let's see what this is. The first invariant you will see in this course. So we will define what's the sign of a cycle. Okay, this is an invariant of a cycle. So an invariant of a cycle sign, okay, we define it as a +1, or we say that it's even if it can be expressed as an even number of transposition. Okay, and -1 odd, or we say it is odd if it can be expressed as an odd number of transposition. Okay. So why do I say this is an invariant of a cycle? Because no matter for a cycle, no matter what kind of expression you pick, it is either can be written as a product of even permutation or odd permutation. Okay, you can write it as, for example, okay, let's talk an example. Okay, I don't talk abstract stuff. I talk example. I'm quite practical. I'm a practical person in the abstract world. Okay, so you see, this is a 1, 2, 3, right? 1, 2, 3 can write as a product of 2. Okay, I also can write as a product of 4. I also can write it as a product of 6. Right? I just put a lot of transposition that compose to identity. Okay, so no matter which different expression you pick for a cycle, the sign of this cycle is always 1. So this is an invariant of the cycle. Okay, makes sense? Makes sense, huh? But this is a theorem that need to be proved. Okay, except this, I will show you next week. Okay, when you are fresh. Okay, yeah. So what? Next. Next. So actually, there's an equivalent way to formulate the symmetric group, and you should have seen this before. Okay, you should have seen this before in your linear algebra class. Okay, you should remind yourself about the what do you call that? Reduce row echelon form. You have how many steps? How many process you can take? Basic operation. Huh? 3. What are those? You can scale the equation. Okay. You can add or minus the equation, and then you can swap the equation. Okay. So these 3 can be realized as an elementary matrix system. Okay. So in particular, in our case here, we are interested as a swapping row. Okay, swapping the row. So what do I mean by that? So if we attach each indexes, 1, 2, 3 up to n by the standard basis E1 up to En, then what is the cycle actually? What happens if you swap the order of basis? What can you realize it as? It is a linear transformation. Okay, a linear transformation in a finite dimensional vector space is always a matrix. Okay, and what kind of matrix is it? It is actually a what kind of matrix if you swap basis? No, it's a permutation matrix. You know what's the permutation matrix is? No, don't know. Forgot, don't know. Never introduced. Okay, so what's the definition of a permutation matrix? And I know your class like example. Let me give you example first and then I'll So I claim that this is a permutation matrix in M2. Okay, what in particular, what does this matrix does? This matrix, what does it does? Sends E1 to where? Sends E2 to where? What is E1 and E2 in this case? Okay, I tell you, I'm an abstract person which is very practical. So when I say E1, E2, this really means some vector. How to write down this vector? Standard basis. 1, 0, and 0, 1. Okay. So what happened to 1, 0, and 0, 1? Under this map. E1 gets sent to where? 0, 1, right? Okay. And then 0, 1 gets sent to 1, 0, which means E1 to E2, E2 to E1. So they swap. Right? So this is the permutation matrix. So how we encode this structure here? Okay. So in the permutation matrix, each row and each column should only have 1, 1. Okay. Each row and each column only can have 1, 1. Okay. Makes sense? So a permutation matrix has 1 in each row and each has only 1 as a 1 in each row and each column. Is this English correct one? In each row and each column, you only have a 1, 1. Is this correct? Is this English correct or not? Has a 1, has only a 1 in each row and each column. Okay, for example what? I don't want something like 1, 1, 0, 0. Okay, this is a non-example. Okay, we cannot have this thing. Each row, each column must only have 1, 1. Okay. All right. Yeah. Okay. So remember what happened. What's the effect of doing row operation, the permutation to the row reduction on the determinant? Do you remember? Forgot. So determinant. So question is, so determinant of a permutation matrix on A. What's this effect? Anyone recall now? What's the effect? Negative, right? Okay, depend on the permutation. You either get -1 depending on P. How should I write it? Okay, maybe I write -1 if P is just swapping rows. Okay, in other words, it is a transposition. Okay, if you transpose it, you get a -1 contribution. Okay, yeah. Okay, so you see, is this somehow related to the sign we introduced just now? -1 if it is odd. Okay, so in particular, a transposition itself is odd. Okay, so there's a minus sign. So this sign is recording the transposition. Okay, how many transposes you did? Did you did oddly or you did evenly? Okay, and then this in the linear algebra theory, this -1 drop out from the. Okay, so this is the equivalent way to formulate a symmetric group. Okay. So you see, so they are equivalent. One I define on number, one I define on a vector space. Which one you think is more abstract? Number is more abstract or vector space is more abstract? Vector space is more abstract. I thought you live in a vector space. Isn't it you live on a vector space? Yeah. Right. So you can play around with vector space. Okay. But number can really represent a lot of things. Okay. I not only can attach vector space on this number, maybe I can attach other stuff on this number here. Okay. So what I want to convince you is really you already step into an abstract world, but you don't know about it. Okay. Since young, you are taught what is 1, 2, 3, 4, 5, but what is really 1, 2, 3, 4, 5? Okay. Maybe this father use apple, that father use pen, the other father maybe use what? What did your father use to teach you about number? Huh? Huh? KFC. Chicken. Wow, so many chicken. So I think you are a farmer. Right. Okay, you see, 1, 2, 3, 4, 5 means different things to each one of you. Okay, but every one of you know what is 1 plus 1, 2 plus 2. How come? Right. So you are actually stepping into this abstract world. Okay, but without knowing it. Okay, let's go on. So we will touch a subgroup definition today. Good. So what's the subgroup? So please listen carefully because in your assignment, you need this definition. So what's the subgroup? So we already say sub, right? So it's like a subset. Okay, so first we start with a subset. Subset H of the group G. So we start with a group. Group is a set, so we can consider the subset. Okay, subset of a group. So when is subset of a group? Okay. This is what we want as a subgroup. Okay. So a subset H of a group is a subgroup. Okay. If it has the following property. Remember the quiz I gave yesterday? Not yesterday, 2 days ago. Okay. Some subset is not closed. Okay. So we are interested in a closed subset. So first, it must be closed. Okay. So if, meaning if A and B in my subset, okay, I still want to compose them together. Okay, it must not jump outside my subset. Okay, it still stay inside my subset. So if A and B in H, AB has to be in H. Okay, but this is not always true, right? Last time we gave you the example. Still remember the example or not? What example is it? R/0, and then which subset is not closed under the induced operation? Plus n plus 1n minus 1. Okay, this is not closed under the induced operation. Okay, so first we want it to be closed. Okay, second, what else? Identity. Okay, identity still lie inside my H. Okay, we still want the structure of the group to happen. And then the other one is of course the inverse. So for every X in H, we have about A in H. A inverse is also in H. Okay, so you can think of it as a group G. Okay, and group G has E. Okay, H must also contain E. Okay, subgroup. Okay, so you cannot pick a subgroup here. No one want this subgroup, want this subset. Not interesting. But later we will see some interesting subset that doesn't contain identity. Okay, not arbitrary subset that don't contain identity. Okay, later we'll see. So subgroup has to contain identity because we want the structure of group. Okay, so notation. Okay, notation. We will write like H is less than or equals to G. Okay, less than or equal. Okay, now your less than or equal no longer a number, is a set. Okay. So this is a subgroup notation. Okay, subgroup notation. This is a very classical. You can find in very classical group theory they use this less than or equal to. Okay. Remember. How about associativity? Group need associativity, right? Why I don't put it in here? Why I don't put it here? Yeah, so you use the composition from the group, from the original group. Okay, you use the composition from the original group. And then this is actually the key point you need to address in your assignment. And I will see how you express it. Any question about it? So the key point here is why I don't include associativity into my definition. Okay, any question? I give you a chance to ask now. Any question? No? You understand? If you understand, you need to write it out in your assignment, okay? Okay, let's keep going. So next, so also we have a proper subgroup definition. So we have proper subset, right? So that means if a subgroup H of G is called proper if H is not equal to G, okay? Or you like to improve our notation, maybe you can write this, okay? If H is a proper subgroup G, okay? And the above is if H is a subgroup of G. Can you see the similarity between set theory and group theory here? Okay, so we still have a set structure in group, but we have more than that. We know how to compose elements. Yeah, we know how to combine elements inside the set. Okay, we don't just regard the set as a separate element. Okay, separate entity in the object. Okay, we can compose object. Okay, groups. Okay, so look at some example. What kind of subgroup is interesting? Okay, so first subgroup is what we call the trivial subgroup. Okay, trivial subgroup is just a group with the identity element. Okay, I think when I first introduced the definition of group, Shuling come up and asked me about this group here, group with identity only. Okay, so this is a subgroup of any group. Okay, any group have this subgroup, which we call the trivial subgroup. Okay, it is trivial because it just has identity. Identity composed with identity has to be identity because there's only one element inside a group. Okay, you can only send it to the identity. You cannot do anything else. Okay, identity has identity must be identity. In this case, why? It's not because it is identity. It's because this set has only one element. There's only one place you can send it to, right? Because for the binary operation, what do you need to do? S cross S to S. Okay, so you take two elements in X, send it to an element in X. How many elements in the set? Only have one. Okay, E times E has to be E. There's no way you can send it to. Okay, so it happens that it satisfies the identity property. So this E must be the identity element for the set. Okay, you understand? Okay. So it's not because I start with identity elements. It is because there's only one choice you can make in this group. Okay? Make it an identity. Okay? Similarly, I can like put A here. If you don't like, I can put A here. But because there's only one choice, this is A has to be the identity, has to satisfy the identity element. Okay. So in particular, every set with one element that forms a group are all similar, are equivalent. Okay. So this equivalent idea, right, later we will make precise. What's the equivalent groups mean? Okay, so what other subset that's interesting? Well, let's see. So for example, in Z6, is there any interesting subgroup or not? Is there any subgroup that's not the original group? So first of all, subgroup need to contain what? Identity, right? So my subgroup must have 0 first. Okay. Obviously, 0, this group is inside Z6. Okay. Anything else other than this trivial subgroup? Let's say we put the 2 here. Sorry. Oh, what's the operation? Good. So now we will consider just plus, okay? Just plus. Last time we said that only Z mod P is a group, right? When we consider multiplication. So we consider plus here. Okay? Yeah, good. So this is a good question. So what's the operation? I need to know. Okay, group is a tuple. It's a set with an operation. So if let's say with 0, I put 2, and these two form a subgroup or not? How to form a subgroup? Closure. Okay, you need a closure, meaning 2 plus 0 have to be in this set. Okay. 0 plus 0 have to be in this set. 2 plus 2 have to be in this. So 2 plus 2 is what? 4. Is 4 in this set or not? No. Okay, I want to make it a group. I add the 4 in. Okay, I add the 4 in. Okay. So 4 plus 4 is what? 8. 8 mod 6 is 2. So I come back to 2 again. Okay, so it's in this set. Okay. How about inverse? Inverse of 0 is still 0. Inverse of 2 is 4. Okay, 4 is in there. Inverse of 4 is in 2. Okay, so everyone have inverse is closed under multiplication. So this form a subgroup. Okay. Sorry, I haven't really explained this notation, but we will do it more precise later. So for now, what does it mean? So in this set here, is generated by this 3 element. Okay, you have this 3 element, and then what you can do, you can compose them. That's all. Okay, you can compose them. That's all. Okay, so this is the subgroup inside Z mod 6. Okay, so this is the subgroup inside Z mod 6. Any other subgroup or not? Do you think? Any subgroup you can find, which is not all of these. 015. Let's try. Let's try. Okay. Y suggests 015. So 1 plus 1 is what? 2. Is 2 in the set? No. So I need to add it in. 2 plus 1 is what? Is 3 in the set? No, I have to add it in. 3 plus 1, 4. 4 is not in the set, so I need to add it in to close it. And then almost you got everything already. So this is the whole set. Okay. Any other different subset or not? Purposes? 0, 3, 0, 3. Okay, let's check. 3 plus 0 is what? 0. 3 plus 3 is what? Yeah, 3 plus 3 is also 0. 6 mod 6 is 0. Okay. Okay, so this is closed. Identity is 0. Inverse. What is the inverse of 3? 3, because 3 plus 3 is 0. Okay, so this form another subgroup inside our Z mod 6. And then I think it's just these two. And in fact, with more tools, we can prove that there's only 2 subgroups for this group. later. Okay. Okay. Let's finish example of subgroup and then we will finish the day. So for example, last time we have R cross R multiplication. Do you remember what this set is? What's this set? Yeah, right, correct. So real, throw away the zero with multiplication because zero is not invertible under multiplication. So there's a set, there's a subgroup here which is rational with multiplication. Okay, also work. And product of rational number is still rational. Okay. And then inverses easily exist. Identity is one. Okay. More. So we got more. For example, C. Okay, in complex number. Okay, we also can consider C cross. Okay, we also can consider C cross. Just throw away C. Just throw away zero. Okay, throw away zero. And then you should check that. Can you find the inverse of A plus BI or not? What's the inverse of A plus BI? You should conjugate, right? Okay, you should conjugate this, and then you will find it. You should conjugate this. One very interesting subgroup inside the C plus is the root of unity. Okay, root of unity. Have you guys seen root of unity? No, no, not root of unity. So, root of unity, for example, I give you an example first. For example, U4. Okay, U4 is what? U4 are all the numbers such that x to the power 4 is 1. Okay, in real. Okay, so sorry, in complex. Because in real, there's only two solutions to this. What are the two solutions? X equals to 1 and x equals to minus 1. Okay, so how to cook out another two roots in complex? X equals to I and x equals to minus I. So this is the four roots. Okay, so a fundamental theorem of algebra says that the roots of a polynomial can be found in the complex. Every root of polynomials can be found in complex number. Okay. Yeah, so these are the four roots. Okay. So there's another way to write down these four roots, right? You can write it as a, what do you call that? Is it the Moivre formula? The Moivre formula? Okay, so you can write it as 2 pi I over 4. Okay, yeah, 2 pi I over 4 times k, where k is starting from 1. Is it starting from 1? Starting from 0, 0, 1, 2. Okay, okay. So un is what? So un is e to the 2 pi I over n times k, where k is going from 0, 1, or 2, and minus 1. Okay, hopefully I don't give the wrong probability. Okay, yeah. So there's another more interesting. Okay, we can take the union of root of unity. Okay, so this union of root of unity form a circle inside our complex plane. Okay, so we can take u equals to the union of un. Okay, union of un. Okay, so it forms a circle, unique circle. Okay, unique circle in the complex plane. So let's imagine this is an imaginary plane. Okay, complex plane. Okay. So U is also a subgroup of C. Next, there's a subgroup of Sn, very important, okay, which we call An. So An are those even permutation. Okay, all the permutation can be written as a even product, right? So even times even, you still get even product. Okay, so this form of group, right? This form of group, and this one very important. What else? For example, in our homeomorphic function, right? Or homeomorphic function. What's the subgroup inside this homeomorphism? Any subgroup or not? Which is non-trivial one, not the whole group, not the identity subgroup. Okay, we can consider the homeomorphism that is differentiable, homeomorphic, and differentiable. Okay, even more restrictive, it is differentiable, not just continuous. Okay, and then we can further going down, homeomorphic plus differentiable, and then twice differentiable. Okay, we can differentiable twice, and then we can go on and on and on and on and on until infinitely many differentiable, which is a smooth map. Okay. Yeah, so these are all subgroup. And then how about GLN? Set of invertible matrix. Okay, that's one very important subgroup you need to know to get into Lie algebra. So the important subgroup is called SLN. Okay, so G represent general, S represent, want to guess? Yes? Huh? Special, yes, special. So special linear subgroup, linear group. It's very special. So how special is it? Special linear group. So you already know that this GLN, the determinant is non-zero. So there must be some condition on the determinant. So special linear group are the set of n by n matrices with determinant 1. With determinant 1. Is this a subgroup or not? If you multiply two matrix with determinant 1, what is the determinant of the product of matrix? Determinant of AB is what? Determinant of AB, two matrix is what? Determinant of A times determinant of B. Okay? Which means 1 times 1, which is 1. How about inverse? Does inverse exist? Does the inverse of a determinant 1 matrix still determinant 1? How to check? How to check it? So how to show determinant of A inverse is 1? How to check this? Huh? Divide? How to divide? 1 over this, and then? Oh, you mean this is true? Is it? This is true. Okay, how is this true? Why is this true? Z, which is the determinant of identity. So determinant of identity is just 1 because it's a product of diagonal. So we settle inverse, we settle closure, we have to settle identity. Identity we already settled just now. Okay, that's all. Okay, closure, identity, inverse. Okay. Okay, any question? Any question before we break? Okay. So next lecture we present a proof and then we'll continue with the subgroup business. See you next week.
Problems and I have some doubts with 2 and 3. Are you already explained?
Oh, okay. Yes, can. Sure. Okay, okay.
你这个好像写反了，
写反了。
因为这个 imply 这个，可是这